Hello. In the last two lessons, we took a detailed look at the universe and then our solar system. And now we're going to take a look at our Earth. We are going to spend a considerable amount of time talking about our Earth. Now, first we will look at the Earth in space. When you look from space, how does the Earth look? The first question that comes to our mind, or at least in the mind of people who lived about 300 years ago, what is the shape of the Earth? You see, a lot of people even now think that the Earth is flat. Now, is that true? What is the real shape of the Earth? In 6th century BC, Aristotle was able to conclude that the Earth is actually spherical using some persuasive arguments. Now, what are some of these arguments? I'm going to take you briefly through these arguments. Now, watch the stars as you travel from north to south. Now, suppose you are here, we're close to the North Pole, and you look at a star in the south. Now, the star looks fairly low in the horizon when you look from there. And as you travel south, and you know a lot of people do that as they travel by ship, as they travel south, the star seems to be going higher and higher. Now, the only way that can happen is that the shape of the Earth is spherical. That means we are going down and down. As you go to south, we are going down and down, which means we will see the star going higher and higher. So that is a persuasive argument that the shape of the Earth must be spherical. Alright? What is the other argument? If the Earth were flat, this will not happen. What will be the observation if the Earth were flat? If the Earth were flat, if you move from north to south, the elevation of the star will remain constant. Well, watch a boat sail away from the shore. This is something you even hear in your elementary school. Well, watch a ship sailing away. If the Earth is flat, you will see the entire ship as it disappears. It will grow smaller and smaller, but you will see the entire ship. But in actual observation, what actually happens is, as you keep observing, the bottom of the ship disappears first, and finally you will only see the ship's mast. And what has happened? The shape of the Earth is spherical. That means the bottom of the ship has disappeared. So that happens only if the shape of the Earth is spherical. All these are very persuasive arguments for the spherical shape of the Earth. Alright. The hull disappears first, and only the top mast and the flags are visible because of the spherical shape. Now, a third way of concluding that Earth is spherical is to rely on analogy. What is the analogy? There is a semi-philosophical argument based on the fact that the sun and the moon are seen to be round. Is that right? When you look at the sun, it looks round. The moon looks round. Therefore, the persuasive argument is that the Earth also must be spherical. In fact, all heavenly bodies therefore could be spherical. Another one, watch the eclipses. When the shadow of the moon falls on the Earth. Well, here is the shadow. When the lunar eclipse occurs, that is, the shadow of the Earth falls on the moon. Now look at the way the shadow of the Earth falls on the moon. The only way the shadow can be appearing like this is because the Earth is spherical. If the Earth were flat, you would see a straight line rather than a curvature. So all these are examples which shows that the Earth is spherical. Is that right? Well, that is the eclipse, when the sunlight is blocked by the Earth, the shadow of the Earth falls on the moon, and since the shadow looks curved, we can conclude that the surface of the Earth is also curved. Well, at the moment we don't need any of these persuasive arguments. We know that the Earth is spherical. Is that right? Well, in geometry, we know that the smallest volume occupied by any geometrical shape is actually a sphere. So when heavenly bodies are formed, because they are moving around and rotating, they will take the smallest possible volume, which is spherical. And of course, all of us now know this is the Earth that we are familiar with, which is a spherical object, and we all know this is what it looks from the space, because we have been shown pictures taken by astronauts from space, so we have no quarrel with the shape of the Earth at all. How about the size of the Earth? How huge, how big is the Earth? How many of you remembers the diameter of the Earth? All right, the diameter of the Earth is 12,756.3 kilometers. For convenience, you can remember it as 12,800 kilometers. All right, it's a good number to remember. And its mass is 5.972 times 10 to the 24 kilogram. Now here we have a beautiful picture of the Earth. The diameter is about 12,800 kilometers. Okay, let's now talk about the Earth's revolution. What does the Earth's revolution mean? Well, the Earth is moving around the Sun. It is revolving. Is that right? Let me see if we can have a look at it. The Earth is revolving about the Sun. Now here I have the picture of the Sun and the Earth. Let's have a look how it revolves around the Sun. Now, how long does it take for the Earth to complete one trip? Well, let's turn it on. Okay. Well, here you have the Sun, and you can see the Earth revolving around the Sun. And of course, the Moon goes around the Earth. Is that right? Now, isn't that a beautiful picture? So the Earth revolves around the Sun. How long does it take? Well, we know it takes 365 days to do that. All right, let's put that away. The Earth is the third planet of our solar system, and it revolves around the Sun in 365¼ days in a slightly elliptical orbit. So the orbit of the Sun, of the Earth around the Sun, is slightly elliptical. Now, what is the word that I gave you for describing an ellipse? It is the eccentricity. When you say slightly elliptical, we say the eccentricity is rather low. If it is a very flat ellipse, the eccentricity is very high. Orbits of comets are very highly eccentric. All right. The elliptical orbit of the Earth varies 147.5 million kilometers on January 3rd. That is the perihelion. I'm sure you'll recall that word. Perihelion is the time when the Earth is closer to the Sun, and the closer distance is 147.5 million kilometers, and when the Earth is far away, the farthest is 150 million kilometers, and that is the aphelion. Now here I have that picture for you. Now this is the perihelion. That is when the Earth is closest to the Sun. That is 147.5 million kilometers. And this is the aphelion, where the Earth is farthest from the Sun, and the distance is 152.5 kilometers. When we normally talk about the average distance of the Earth from the Sun, it is the average of these two distances, which is about 150 million kilometers. Now, there are many people who think that the seasonal variations, summer and winter, occurs because of this. Well, really no, because you know that at aphelion, when the Earth is farther from the Sun, July 4th, that is the summer for us. Is that right? And when the Earth is closer to the Earth, it's the winter time, January 3rd. So, the distance of the Earth from the Sun is not what determines the climates on the Earth. We will talk about that as we go on. The rotation of the Earth has more effect on the climate than the distance of the Earth from the Sun. In other words, it is the rotation of the Earth. Look at that one more time. It is the rotation of the Earth that has more effect on the climate. You can see as the Earth is going, revolving, it is rotating. Can you see it rotating? Yes, it is rotating on its axis. And look at the tilting of the axis. The axis is not straight. It is actually tilting at an angle. It is the tilt of the axis of rotation that actually contributes to the climatic changes. We will talk about that as we go on. Now, winter actually occurs on the northern hemisphere at perihelion, and summer occurs at aphelion. Now, what are solstices? Solstices and equinoxes are caused by the inclination of the Earth's axis to the plane of the ecliptic. Now, there are a couple of things I want you to understand. What is the meaning of the ecliptic? I talked about that. Now, if you look at the plane of the Earth's orbit. Now, what is the meaning of plane of Earth's orbit? Now, suppose, look at the plane surface. If the Earth is orbiting around the Sun, suppose this is the Earth orbits around the Sun, and look at the plane. Now, this is the plane of Earth's orbit. Alright? Now, if Earth's orbit is, say, tilted, you can see that plane is tilted. Alright. Now, that plane that contains the Earth's orbit around the Sun is actually called ecliptic. Now, I'm going to define ecliptic in a slightly different way. Alright? Try to understand this. When you look at the motion, we don't feel that the Earth is moving, but we feel that the Sun is moving. So we are going to define ecliptic as the plane in which the Sun moves. You see that? We are on the Earth, we don't see ourselves moving. Although, watch this again, although ecliptic is the plane of the Earth's orbit around the Sun, it can be defined to mean the same thing as the orbit of the Sun around the Earth, although Sun does not move around the Earth. Alright? So, for the present, I am going to define ecliptic as the orbit of the Sun around the Earth. Now, if you can look inside here, can you see that small thing? That small thing is actually the sun. And inside you have the earth. And for us, it looks like the sun goes around the earth. You see that? And the plane taken by the sun going around the earth, it is that plane that we call the ecliptic. So, the solstices and equinoxes are caused by the inclination of the earth axis to the plane of the ecliptic. You see, if this is the earth's axis and the plane of the ecliptic, if this is the ecliptic, you can see there is an angle of inclination between the ecliptic and the axis of the earth, and the seasonal changes are actually caused by this angle of inclination. Now, summer solstice happens when? It's the first day of the summer, of the season of summer, and it is at that time that the northern hemisphere, sunlight is falling directly on the northern hemisphere at that time. Now, how does it happen? Because of the tilt of the Earth's orbit. Let's see if we can have a look at that one more time. All right. Now, I hope you can see the tilt of the Earth's orbit. You see, the Earth's axis is not straight like this, it is tilted. And because of the tilt, now you can see at various times the direct light from the sun falls on the earth at different parts, and you can see the season, you can see the amount of light falling now is greater at the northern hemisphere. Okay, let me put that off now. So, summer solstice is the first day of the season of summer, and that is when the sun's light is directly on the northern hemisphere. On this day, that is June 21st, that is the time the sun will be at its northernmost part. On June 21st, the sun is the farthest to north, and the length of time between sunrise and sunset in the northern hemisphere will be the longest. And if you happen to live in the Arctic Circle, you will have 24 hours of daylight. Isn't that nice? Well, it's very boring. And at that time, if you happen to live at the Antarctic Circle, you have 24 hours of darkness. Alright, what is this winter solstice? Winter solstice occurs when the sun is at its southernmost part. Now, sun's light is falling directly on the southern hemisphere, and that happens on December 22nd. On this day, December 22nd, the sun is farthest south, and the time between sunrise and sunset in the north for us is the shortest. Now, what is the equinox? I want you to understand the meaning of the equinox very well. Now, an equinox is when the sun is directly on the equator. So you can see the sun wanders from south to north, and on its way from south to north. Now, at this time, when the sun is at this point, the sun's light falls directly on the equator. And now, if it's going to the north, now that's the summer solstice. Back on the equator, that's the equinox. And now the winter solstice and the equinox. So how many equinoxes occur in 1 year? As the sun moves between its south extreme and north extreme, it crosses the equator twice a year. So 2 times a year, when night and day are about the same, the length of the day and night are the same. The sun is crossing the equator and it is an equal distance from the North Pole and the South Pole. Alright, now look at an animation of the motion of the Earth around the sun. The revolution of the Earth around the sun. You can see this is the winter solstice, and you're coming on to an equinox. Alright, and then the summer solstice. You are coming down to the second equinox of the year, and that's the winter solstice, and the Earth is continuing there. That's today, is that right? Okay. Spring equinox is the first day of the season of spring and the beginning of the long period of sunlight at the pole. And that is the spring equinox when the Earth is here. Autumn equinox occurs, that's the first day of the season of autumn and the beginning of a long period of darkness at the pole. When I say the pole here, I specifically mean North Pole, because you see, majority of the world's population live on the northern half of the Earth. You have only a very small population at the southern half, part of South America, Australia, and so on. Alright, so you got the spring equinox of March 21st, autumn equinox is September 23rd, we just passed it. So we are actually now here. The marking that you saw here today is not really true, because I took this picture some time ago. So this is not today. Our today is somewhere here. We just passed the autumn equinox. We are now in autumn, is that right? In the fall. Well, what is celestial equator? Alright, try and pay attention to it, because I want you to imagine things. And there is a limit to which I can actually show you things. Now, I want you to look at this model. Let me see if I can show that to you. Well, here I have the model of the Earth that I just showed you earlier. Now, can you see the Earth sitting inside a plastic dome? Now, what is this plastic dome? If you stand outside and look, don't you see an umbrella-like thing? That is a dome. And that is enveloping the Earth all over. And that is what is constructed here. And this is called the celestial sphere. So, when you look up from any point, you know that you are under a celestial sphere. Can you imagine that? You see, the Earth is the small sphere inside, and the transparent plastic is the celestial sphere. And what is the celestial equator? Now, if you can look at the Earth's equator, you know where the Earth's equator is? Well, let me see if that can be visible. Now, the Earth's equator is, well, let's take our big model and look at the Earth's equator. Well, if this is the big model, the Earth's equator is this line that divides the sphere into 2 halves. In the same way, you can look at the equator there. If you stand on this equator, on the Earth's equator, and look up, you see the celestial sphere? Well, what you see directly above you is the celestial equator. So what happens is, you can imagine an equator for this celestial sphere. and that occurs directly above the Earth's equator. Alright, let's see if I can show that to you. Now, suppose this is the Earth's equator. Alright, now if you stand on the equator and look up, you see the celestial sphere, and this is the equator of the celestial sphere, the outer circle. That means if you are standing here on the Earth's equator, directly above you will be the celestial equator. Alright, I hope you got the picture. Let's move on. Now here I have a picture of that. Now this is the Earth, and look at the Earth's equator. If you stand in there, the circle, the big circle directly above you is the Earth, is the celestial equator. Alright? So the Earth's equator, the celestial equator, the Earth's North Pole, Earth's South Pole, and what you see here is the celestial sphere. The celestial sphere has the North Pole and the South Pole. We call this the South Celestial Pole, and this is the North Celestial Pole. So celestial equator is a line on the celestial sphere directly above the Earth's equator. Like the equator of the Earth, the celestial equator lies halfway between the two poles. So this is the North Celestial Pole, this is the South Celestial Pole. The celestial equator is halfway between the North and South Celestial Poles. Okay. Equinoxes. Well, you remember the equinoxes we talked about? Equinoxes are the time when the sun comes directly on the equator. And now, we are now going to define the equinox using the two concepts we talked about. One is the ecliptic. What is the ecliptic? Ecliptic is the plane of the sun's orbit. When I say the sun's orbit, you must understand it is the Earth's orbit around the sun. But for convenience, I'm going to call it the sun's orbit. Why? Because we see the sun going around the Earth. So ecliptic is the sun's orbit around the Earth, and the celestial equator is the equator of the celestial sphere. Alright, equinoxes occur when at points where these two cross. Now let me see if I can show that to you. Now first of all, understand this. Equinoxes are points on the celestial sphere where the ecliptic, the path of the sun, crosses the celestial equator. Let's see if I can explain that on this diagram. You can see the blue line represents the ecliptic. That represents the path of the sun around the Earth. And the brown line represents the celestial equator. And you can see at 2 points these two planes cross. So this is the position of autumnal equinox. That is the time when the sun's rays fall directly on the equator. And this is the position of the vernal equinox. Well, let me see if I can show that to you on my model here. Try and watch carefully. Alright, now watch the celestial equator. Now, can you see this line where I'm running my fingers? That's the celestial equator. And this celestial equator is directly above the Earth's equator. And look at the motion of the sun. The sun is that little yellow ball. See that? That little yellow ball is our sun. And I'm going to make it move around the Earth. And this plane described is the ecliptic. And look where the ecliptic is now going to cross. The ecliptic is now crossing the celestial equator. Can you see that? The ecliptic is crossing the celestial equator here. There you are. Now this is the position of an equinox, and as it goes the other way, you can see the ecliptic is now crossing the, well, over here it's again crossing, there you are, it's crossing the celestial equator. So that is an equinox, this is an equinox. So what is the definition of equinox? Equinoxes are points on the celestial sphere where the ecliptic, the path of the sun, crosses the celestial equator. Again, this is the celestial equator, the red line, and blue line is the ecliptic, that is the orbit of the path of the sun around the earth. And at 2 points they cross, and they are the equinoxes. Summer solstice occurs when the ecliptic is 23.5 degrees north of the celestial equator. So you can see this is the summer solstice, this is the ecliptic. It is now, you see, look at the horizontal where my pointer, the rod is. Now the ecliptic now is at an angle of 23 degrees north. There you are. So summer solstice occurs when the ecliptic is 23.5 degrees north of the celestial equator. That's the celestial equator. There you are. And the winter solstice occurs when the ecliptic is, you can see that's the ecliptic, is 23.5 degrees south of the celestial equator. You must understand both these are planes. Well, let me see if I can show that one more time to you. You must understand both these are planes. If this plane represents the celestial equator and this plane represents the ecliptic, then you can see the angle between them. This is now 23.5 degrees south. That is the winter solstice. And when it is 23.5 degrees north, that is the summer solstice. Alright. Let's now talk about the rotation of the earth. You see, the earth not only revolves around the sun, but along with that it is also rotating. Alright, so the earth is rotating. In 1851, Jean-Bernard Foucault suspended a 67-meter, 28-kilogram pendulum from the dome of the Pantheon in Paris. Now, how do we know that the earth is rotating? Is there any indication that tells us that the earth is rotating? It is the experiment done by Foucault that actually proved that the earth is rotating. And this is the setup he did. He suspended a great big pendulum. You see, a pendulum, what is a pendulum? A pendulum is a great massive ball suspended by a string and set it into oscillation. You see, the pendulum keeps on oscillating. Now, Foucault made a very interesting observation. He found that the plane of motion with respect to the earth rotated slowly clockwise. Now, if you look at the pendulum that is oscillating like this, can you see my pendulum? I'm trying to see if I can show that pendulum to you. There, you got the pendulum oscillating. Now, if it oscillates in a different plane, you can see I'm showing you different planes of oscillation. Now, what Foucault observed is that the plane of oscillation slowly changed. Now, how can the plane of oscillation slowly change? The only explanation is the earth below the pendulum. You see, the pendulum is oscillating, and the earth below, because of its rotation, is moving away. And that makes the plane of the pendulum to rotate. Well, I don't know whether you understood it. Well, I'll see if I can show you an animation. Now, this precession, what is the meaning of to precess? You see, if this axis, this is an axis, it can rotate. I'm actually rotating it. And look at the way the axis is precessing. This kind of a motion is called the precessional motion. So what you see the pendulum is doing is, the plane of the pendulum is precessing, the plane of the pendulum is precessing clockwise. Alright? So the precession of the pendulum suggests that the earth below it is rotating. So the precession of the pendulum is more pronounced at the poles than at the equator. Why? Because if you go to the poles and suspend the pendulum there, the rotation, the earth moves much faster away from the pendulum at the poles than at the equator. I suppose you can picture that. Now, let me see if I can show you an animation of this. Now, I would like you to look at these two animations. Now, look at the pendulum oscillating at the top. And look at the plane of oscillation. After some time, you come down and look at the pendulum. Its plane of oscillation has changed at the bottom. That means the earth has moved away from the pendulum. The earth has rotated away. That means the plane of oscillation of the pendulum is changing clockwise. That shows that our earth is rotating. Alright? I suppose you can now see the oscillations of the pendulum. Alright, let's do away with this and talk about the rotation of the earth. Now we know that the earth is rotating. Now here is an illustration of that. This is an experiment done by John Bird in University of South Wales in Australia. They went to the South Pole and set up this pendulum, and they clearly observed the rotation of the plane, or the precession. I want you to understand the meaning of precession, because I'm going to introduce that again to you later on. So Mike Town and John Bird set up this pendulum at the South Pole. The precession of the pendulum is due to the rotation of the earth below it. More evidence that earth rotates is provided by objects that move across the earth. Now, you see, if the earth is rotating, when the earth is rotating, tell me, what part of the earth is where I'm pointing now, or near the poles? Where, if a person is standing here, another person is at the equator, which of those two will be moving faster when the earth rotates? You see, as the earth rotates, this person takes a very long time to complete one circle, whereas that person completes one full circle in a short time. That means this person near the pole will be moving much faster than the person at the equator. That means, imagine that you are walking from, can you see where I'm pointing? Imagine that you are walking from the equator to the poles. So, as you walk towards the North Pole, your speed of rotation is going to increase. Now that means you can never go straight across. When you go from the equator to the pole, your path is going to be shifted to the right. You see that? You understand that? Because as you go towards the pole, your speed will become faster and faster. So your course, your path will be shifting towards the right. And that is an observed phenomenon, and that also is a clear indication that the Earth is rotating. Earth has greater rotational velocity at the equator than at the poles. Now that means if an object is moving from the equator towards the pole, it will veer towards the right. The same way, an object moving from the equator to the south will veer towards the left. That's right. Now, this effect is actually called Coriolis effect. An object moving from the equator to the North Pole will veer towards the right, and an object moving from the equator to the south will veer towards the left, due to the differential speed of rotation at different parts of the Earth. So this apparent deflection caused by the rotation of the Earth is called Coriolis effect. As air moves from high to low pressure in the northern hemisphere, it is deflected to the right by the Coriolis effect. In fact, many of the weather patterns are produced by this effect. And in the southern hemisphere, air moving from high to low pressure is deflected to the left. Let's now talk about the precession of the Earth as it rotates. You see, you know that the Earth's axis is something like this. It is not straight. The axis of the Earth is tilted, and as the Earth keeps rotating around the Sun like this, its axis slowly precesses. In other words, the axis makes this kind of a motion. Its axis is precessing. Now, what is the period of that precession? How long does the Earth take for the axis to complete one precession? Actually, it is a very long time, so we don't really notice it. It takes 26,000 years for the Earth to complete one precession. And we, people like us, who live only an average of 75 years, this 26,000 years is a very long time. So, if the Earth's axis is pointing like this today, in another 13,000 years, Earth's axis will be pointing like this. What does that mean? If Polaris is our pole star, you know what a pole star is? A pole star is the star you see directly above the North Pole. And that star is called the Polaris. Now Polaris is our pole star. Now, in 13,000 years, when the axis of rotation is like this, Polaris will not be the North Star anymore. It will be some other star. So, there is profound effect caused by the precession of the Earth's axis. The Earth's rotation axis is not fixed in space like this. Like a rotating toy top. Have you seen a toy top rotating? There, I have the picture of a top. If you allow this top to rotate, to spin it and rotate, it will go along with its spinning, its axis will do this kind of motion. That is called the precessional motion. And the axis of the Earth complete one precessional motion in 26,000 years. That's right. This is the axis. If it is now like this, in 13,000 years, the axis will point this way. In 26,000 years, the Earth will complete one precessional motion. So in about 12,000 years, the bright star Vega will be the pole star. You can see now The pole star is the star you see somewhere here, that is the Polaris. And in about 12,000 years, it is the bright star Vega, which is here, that will be the pole star. But we will not be there to see that. Is that right? Since the rotation axis is precessing in space, you see, it's going to create more problem for us. Because the rotation axis is precessing, that means the celestial equator is also precessing. What does that mean? It means the points where the celestial equator and the ecliptic will meet, those points where they meet are also moving. What does that mean? It means the times of the year when we have winter, summer, spring and autumn are also changing. You see how complex all these situations are. So, since the rotation axis is precessing in space, the orientation of the celestial equator also precesses with the same period. Now, this means that the position of the equinoxes is changing slowly with respect to the background. If the autumnal equinox occurs at September 23rd now, after about 10,000 years, well, after about 1,000 years, it may be October 23rd, because the point where the ecliptic and the celestial equator cross will keep shifting. After about another 1,000 years, it may be November 23rd, and so on. And so, in about 10,000 years, winter will occur in July and summer will occur in January. That's funny, isn't it? But that's going to happen, but we will not be there to witness it. You see, our lifespan is so small compared with these kind of large time scale. All right. Because of the precession of the equinoxes, the vernal equinox moves through the constellation of the zodiac over the 26,000. Now I have a picture of that there. Here I have the celestial equator, and this is the equinox. And now this is the vernal equinox. And at the moment, the vernal equinox occurs in the constellation called Pisces. That is the cluster stars there. And now, as the precession continues, the orientation of the celestial equator will change. That means after about 3,000 or 4,000 years, the celestial equator will cross the ecliptic in the constellation of Aquarius. This point where they meet now will be somewhere here. Now, presently the vernal equinox is in the constellation Pisces, slowly approaching Aquarius. So, in about 2,000 to 3,000 years, this vernal equinox will be in the constellation Aquarius, and it will keep going around, completing one circle in what length of a period? 26,000 years. Let's now talk about locating a position on the surface of the earth. You see, if you want to locate a position on a plane surface like this, what do? We use an x-axis and a y-axis, and we know how to locate a point by using the x and y values. But you cannot do that on a spherical surface. On a spherical surface, to locate a position, you got to be more creative. So let's see how we can locate a particular position on the surface of the earth. All right. First, let's talk about latitude. Latitude, lines of latitude. You see, just like the x and y axis on the plane paper, we will use lines of latitude. They are circles, you see. In order to locate positions on a circle, on a sphere, we need to draw circles on the sphere. So in place of x and y axis, what we're going to do is we're going to draw circles where we can draw horizontal circles and vertical circles. And where these two meet, we can locate a position. Now, the circles of latitude or lines of latitude measure north-south position between the poles. They are not actually straight lines, is that right? They are circles. You see, these are circles of latitude. And the equator is 0 degrees latitude. As you go towards the north, the latitude increases north. As you go to the south, the latitude increases to the south. The equator is defined as 0 degrees. The North Pole is 90 degrees north and the South Pole is 90 degrees south. Lines of latitude are all parallel to each other. Is that right? If you take those lines of latitude, those are circles like this, and each is parallel to the other. In other words, if you take any of these circles, they are all parallel to each other. Therefore, these lines of latitude are also called parallels. Suppose I say 30-degree parallel. What does that mean? 30-degree parallel is this line. You see, let's go and say 10. Well, 30-degree parallel will be somewhere here. Is that right? Yes. Okay. 1 degree latitude is 111 kilometers. So this is 0 degree latitude. You go 1 degree north, you have traveled 111 kilometers north. So you can now calculate what is the distance from the equator to the North Pole by multiplying 90 degrees by 111 kilometers. Is that right? Okay. Alright, we talked about latitude. Lines of latitude are horizontal circles. Alright? Now, longitude. Longitude are also called meridians. They are vertical circles. So, lines of longitude or meridians run between the north and south poles. So, the longitude lines run from north to south and goes around. They are also circles. You see? Lines of longitude are also circles. Now here we have lines of longitude. It runs from the North Pole to the South Pole. But they are not parallel. But one characteristic is each longitude line is the same length as the other, because each is drawn from the North Pole to the South Pole. Now, and they measure east-west position. Now, therefore, you can see when you talked about the latitude, it's easy for us to decide where is 0 degrees latitude, the equator. Now, how do we decide where is 0 degrees longitude? Well, it comes with the old saying, might is right. Now, people who are the strongest, who have the most bigger voice, will get to decide where is 0 degrees longitude. And tell me, in the ancient days, who are the people who used to travel a lot, who used to be scientifically more advanced? Well, obviously they were the British people. So they got to decide where is 0 degrees longitude. The line of 0 degrees longitude is called the prime meridian. The prime meridian. That's the prime meridian there. And it runs through Greenwich, England. Alright, I'll show you that in a minute. meridians to the west of the prime meridian. So these are meridians to the west of the prime meridian are measured in degrees west, and meridians that are to the east of the prime meridians are degrees east. So the longitude positions are measured degrees west or degrees east from the prime meridian, which is 0 degrees longitude. Latitude is 0 degrees at the equator. As you go to the north, you measure degrees north or degrees south. Longitude, prime meridian is 0 longitude. You measure it degrees east or degrees west. Each meridian is the same length as the other. The position of any place on the surface of the earth is where the longitude and latitude. Yes, once you know the longitude and latitude, you can locate any place on the earth. Can you take a globe and determine the longitude and latitude of your location? Well, if you can see this, can you see where I'm pointing? Now, this is Florida where we are, and this is 20 degree north latitude. This is 30 degrees north latitude. So our latitude is between 20 and 30. It's about 26 degrees latitude. So we are 26 degrees north of the equator. And longitude, you see the prime meridian is this, where I'm pointing. Let me see if I can show you. This is the prime meridian that passes through Greenwich, England. And we now go west, is that right, from the prime? How many degrees? Is marked here 45, 50, 55, that's 90. So we are between 60 degrees, 75 degrees, between 75 and 90. So we must be about 82 degrees west. So about 26 degrees north, 82 degrees west is our position. So you can actually locate any position once you know the longitude and latitude. Latitudes near the equator as referred to as low latitude, and latitudes near the poles are high latitude. The parallel of 23.5 degrees is called the Tropic of Cancer. Well, Tropic of Cancer will be somewhere here, 23.5 degrees north. And what is the importance of Tropic of Cancer? That is the line directly above where the sun will be seen at the summer solstice. And that is the characteristic. And the parallel of 23.5 degrees south is called the Tropic of Capricorn. So the Tropic of Capricorn is in the south. That means between the two winter and summer solstice, the sun will be traveling between 23.5 degrees south and 23.5 degrees north. So these two parallels identify the limits towards the poles within which the sun appears directly overhead during the year. Alright? The parallel of 66.5 degrees over here is called the Arctic Circle, and the North Pole is to the north of that. So this is the Arctic Circle. And similarly, the parallel of 66.5 degrees south is called the Antarctic Circle. Now, these two parallels identify the limits towards the equator within which sun appears above the horizon all day during summer. You see, when the sun is at the north, In the North Pole, you have sunlight 24 hours a day. We will now talk about measuring time. Now, what do we do to measure time? Time is measured using an event that occurs in equal intervals of time. Like that, is that right? Okay. Can you think of an event that happens regularly, that repeats in regular intervals, that can be used to measure time? Well, this is what was used a long time ago. Is that right? Sand clock. The amount of time taken for that bowl to empty each time is the same. But of course we use different time standards and different events. But what is it that we can actually dependably use as a means of measuring time? Interval between two successive events that repeat in regular intervals is used as a standard for measuring time. And since ancient time, the repeating events of rotation and revolution of the earth have been used to define day, month, year and season. So it's our earth that gives us all these facilities. The revolution and rotation of the earth are periodic. It repeats in regular intervals. 4,000 years ago, Babylonians used astronomical motions for keeping time. In fact, they used the motion of the sun against the background of stars. You see, the background of stars is assumed to be fixed. So if you now use the motion of the sun, when you say the motion of the sun is caused by the rotation of the earth. So you must understand that. So the motion of the sun against the background of fixed stars was used by Babylonians, and that time was divided into 12 months. That is the yearly journey of the sun. The yearly journey of the sun with the fixed background of the stars. Babylonian year was 360 days, which was divided into 12 months. In addition, Babylonians invented the week and divided the day into hours, minutes and seconds. So Babylonians were way ahead in terms of defining time and measuring time. Now today, it is common knowledge that the earth rotates as it goes around the sun. Now, the celestial meridian, what is a celestial meridian? Now, earlier we defined celestial equator. Celestial equator is the equator of the celestial sphere. Now remember, meridian is a line that passes from North Pole to South Pole, and that will be at right angles to the equator. Is that right? Now, when you stand on the earth and look up, you can see there will be a meridian on the celestial sphere that goes directly above you, and that is called your celestial meridian. In other words, if you are on at any part of the earth, when you stand there and look up, you will see a meridian going directly above you from north to south on the celestial sphere, and that is your celestial meridian. Now remember, if you go towards the west, your celestial meridian will also go west. Is that right? Because the position of an individual determines the position of the meridian. So you must understand that clearly. The celestial meridian is a great circle on the celestial sphere that passes directly where you are and continues around the earth through the celestial North Pole and the celestial South Pole. the movement of the sun across the celestial meridian defines the noon. So you can see, as the sun rises, it moves right up, and when the sun is directly on your celestial meridian, that is called the noon time. 12 noon is the time when the sun is directly above your celestial meridian. Alright? Now, the instant of noon at any particular longitude is called the apparent local noon. Why is it called the apparent local noon? Because when we have noon right here, somebody else far away has not got noon yet. You see, the sun reaches each places on the west a little later. That means the apparent noon keep changing with the position of the sun. Now the morning hours before the sun crosses the meridian, as the sun rises and it rises and reaches the meridian, your meridian, the hours before it reaches the meridian is called the anti-meridian. That's what we call AM. 9 AM, 9 o'clock anti-meridian. And similarly, the time of the hours after the sun has crossed the meridian is the post-meridian or PM. So, once again, when the sun is directly above, your meridian, that is noon. Now, in the morning before it reached the meridian, this is anti-meridian AM. Now, this is the noon, and this is the post-meridian PM. Alright? Now, very often people make the mistake of writing time as 12 AM or 12 PM. You see, 12 o'clock doesn't belong to anti-meridian or post-meridian. So you must distinguish by saying, is it 12 noon or 12 midnight? Alright, so next time you want to speak of 12 o'clock, it is not 12 AM or 12 PM. It is 12 noon or 12 midnight. Alright. The ancient Babylonians used a vertical rod called a gnomon to measure the shadow that moved as a result of the position of the sun. You see, a gnomon is something like this. Now, as the sun moved, the shadow of the gnomon will change. You can see now, what time is it now? It is 12 noon. Alright, now we're going on to PM hours. The shadow is going to the right. You see that? So, ancient Babylonians used this. Well, even when I was a kid going to school, I used a gnomon to measure my time because I did not have a watch. We did not have a clock at home. And I could measure time within 5 minutes. I never got to school late. Well, this is a gnomon, and you can see how the shadow of that will move. The gnomon eventually evolved into sundial. Now here you have a sundial. That is the same thing as the gnomon. You can see the shadow moves, and you can actually label the dial for reading the time. Now the sundial measures the time by the position of the sun in the sky at any time. The most commonly seen designs, such as the ordinary or the standard garden sundial, cast a shadow on a flat surface marked with hours. You can see here, this is the flat surface, that's the shadow, and you can mark it with the hours to read the time of the day. And here I have a more sophisticated sundial, and we have them in all kinds of makes and models. So as the position of the sun changes, the time indicated by the shadow also changes. Okay, sundial measurements fluctuate throughout the course of the year due to the changes in the speed of the Earth in its orbit and the tilt of the equator with the ecliptic. Now, while sundial shows the apparent time, clocks measure uniform standard time based on the mean solar time. What is the definition of that? A day is defined as the length of time required for the Earth to rotate once on its axis. That is the definition of the length of the day. And I'm going to define two types of day. A sidereal day is the interval between two consecutive crossings of the celestial meridian by a particular star. You see, your celestial meridian will make one full round during the day. Now, you keep watch on a star, and then what is the time taken for you to come back about that star? You see, that is one day. That is called a sidereal day. A sidereal day is the interval between two crossings. You have the fixed star there, and what is the time taken for you to rotate completely once and come back against that star again? That is a sidereal day. Whereas what is the apparent solar day? The apparent solar day is the interval between two consecutive crossings of the celestial meridian by the sun. You see, you got a celestial meridian. The sun crossed it now, and now the sun is going to come back. The interval between these two is an apparent solar day. So distinguish between a sidereal day and an apparent solar day. While the mean solar day is 24 hours long, a sidereal day is 23 hours, 56 minutes, 4 seconds. So what we are using is not the sidereal day for our measurements. We use the apparent solar day. Let's talk about the time zones. Everybody is familiar with that, is that right? Why do we need different time zones? Because the sun comes directly above, or the sun comes directly on your meridian depending on where you are. As you go to the west, the sun comes directly on your meridian later and later and later. Therefore, we need to have time zones in order to know what time is at different parts of the world. The 0 degrees longitude line runs from the North Pole to the South Pole, passing directly through the old Royal Observatory building at Greenwich, East London. Well, I have been lucky enough to live there for 3 years in Greenwich. I lived and taught in that place for 3 years. And that is where you have the prime meridian. And meridians to the west are degree west. Is that right? So when you say GMT, 0 degree GMT, that is when the sun is directly above the prime meridian. So it is the basis for timekeeping and navigation throughout the world. The prime meridian is the basis for timekeeping throughout the world. There, this is the prime meridian. This is the old Royal Observatory. It's a beautiful, nice place to go to. When you go to England, go and visit this place. There is an old Second World War ship there called the Cutty Sark. I'm sure you can buy whiskey called the Cutty Sark. Is that right? Yes. But apparently last year, Cutty Sark caught fire, and I'm sure they are in the process of restoring it. So this is the Greenwich Meridian. And look at the time zones. Now, where is 0 degrees? This is the 0, is that right? That goes through Greenwich Meridian. There we are. That's England. That's the prime meridian there. And as you go to the west, each of these is drawn in intervals of 1 hour. So if you notice, the United States, how many time zones do we have? We have 3 time zones: Eastern Zone, Central Zone, and the Western Zone. So given a 24-hour day, 360 degrees longitude around the Earth, is that right? If you go around, it is 360 degrees. Therefore, how many degrees are there in 1 hour? Each hour is 15 degrees. You go from 0 longitude 15 degrees west. That is 1 hour difference. 30 degrees west, that is 2 hour difference, and so on. Now, the individual time zone boundaries are not straight. Well, why not? Because for local preferences, you make your time zone to suit you. So you have time zones like this, chosen by local population. Now, 180 degrees meridian is arbitrarily called the international dateline. Now, I showed you here. Now, this is the 0 degrees longitude. The 180 degrees will be directly opposite to that. If I rotate the globe through 180 degrees, I get 180 degrees longitude. And this is called the international dateline. You know why it's called the international dateline? Because when you cross that line, you either gain or lose a day, depending on whether you cross from west to east or from east to west. All right? So this is the international dateline at 180 degrees. A traveler crossing the dateline gains or loses a day, just as crossing a time zone results in gaining or losing an hour. Isn't it? When you go from New York to Los Angeles, do you gain or lose time? Well, you go at 8 o'clock, you probably arrive at 8 o'clock. You probably don't gain any time. You probably lose time. Is that right? That's right. A person crossing the international dateline westward, if you go west, will gain a day, while a person traveling eastward will lose a day. You see, when you travel from New York to Los Angeles, you are traveling west. You actually gain time. How? You start at 8 o'clock from New York, you land at 8 o'clock Los Angeles. So you're actually gaining time. You really haven't spent any time. So if you go west, you gain time. If you go east, you lose time. Well, there's a good book, I don't know if anybody has read it, Around the World in 80 Days. It's the story of a man who put a bet with his friends that he will go around the world in 80 days. And apparently when he went west and came back from the east, and he was keeping his time, and he thought he lost his bet because according to his count he was late. But at the last moment somebody came and said, "Oh, hey, you are back, so you won the bet." And he said, "Oh no, I lost it." But they said, no, you still have time until midnight today." What happened? Because he traveled west, he gained one day. He didn't know that. Poor man, unlucky man, he won the bet. Well, let's talk about yearly time. A year is the time taken by the Earth to complete one revolution around the Sun. The most common definition of a year is the interval between two consecutive spring equinoxes known as the tropical year. And that is what we use for our calendar. A tropical year is 365.2422 mean solar day. And a sidereal year is defined as the interval of time required for the Earth to move around the orbit so that the Sun is again in the same position relative to fixed stars. But we will not be using that. We are using the tropical year for the calendar. Alright? It is a tropical year that is used to determine the calendar year. The Earth does not complete an exact number of turns while completing one trip around the Sun. And so, that makes that there is need to periodically adjust the calendar to stay in step with the seasons. Otherwise, our seasons will fall at different times of the year. The first such calendar was designed by the Romans. It's called the Julius calendar. Julius Caesar reformed the calendar to have a 365-day year, with every year having a 365-day a year with 366 days every fourth year. The Julian calendar was longer than the tropical year by 0.0078 days, accumulating an error of 13 days by the year 1582. You see how that small difference can then accumulate and cause a big problem. And it is at that year in 1582 when Pope Gregory revised the calendar, making that correction. So that's the Gregorian calendar that we follow. The Gregorian calendar corrects for the accumulator error by dropping the additional leap year 3 centuries out of 4. Did you know that? You cannot have leap year every 4 years. You got to drop a leap year once in 3 centuries out of 4. That means while the year 2000 was a leap year with 366 days, the century years 2100 and 2200 and 2300 will not be leap years. You got to drop leap years in 3 centuries out of 4. So, while the century 2000 was a leap year, the century year 2100, 2200, 2300 will not be a leap year. The next century year that will be a leap year will be 2400. That is to make sure that this small error is taken care of. How about monthly time? The word month has its origin from the moon. The moon completes one revolution about the Earth in 27 1/3 days. This period is called the sidereal month. The rotation of the moon also has the same period. We talked about that. The moon goes around the sun in the same time as it rotates completely once. Because of this, the same side of the moon faces the Earth always. We will never see the other side of the moon. It's called the hidden side of the moon. The ancient concept of a month was based on the synodic month, the interval of time from new moon to new moon. The synodic month is 29.5 days, and the present calendar identifies this as a month. Alright, let's now talk briefly on the eclipses, because when you talk about the Earth in space, any discussion on Earth in space is not complete if we don't talk about the eclipses. Now, what is a solar eclipse? A solar eclipse occurs when the moon comes in between the sun and the Earth, and the shadow of the moon falls on the Earth. So, an eclipse of the sun can occur only on a new moon day. You see that? But does it mean that all new moon days will be the eclipse of the sun? No, because the orbit of the moon keeps changing. When the moon orbits, say, like this, where the moon is here, there will be no eclipse. It happens only when the moon comes directly in between the sun and the earth. The moon's shadow happens to fall upon the earth's surface at that time. We see some portion of the sun's disk covered or eclipsed by the moon. Alright. Now this does not happen every month because the moon's orbit around the sun is tilted 5 degrees to the earth's orbit. And because of that, sometimes the moon will be passing so that it will not come directly between the two. At least twice a year, some part of the moon's shadow falls on the earth's surface and an eclipse of the sun is seen from that region. You see, when an eclipse occurs, not everywhere on the earth will witness it. Only at certain places on the earth will see it. Now, moon's shadow has 2 parts. In fact, shadow produced by any object has 2 parts. You can see when I have the object like this, its shadow is this. Is that right? That is, well, you can see the shadow of, now, where is the shadow? Now, this is the shadow of the object. Now, I can actually see very well here. There is a very dark region and a very diffused region for the shadow. So, a shadow has 2 parts. Now, I don't know whether that will be recorded properly, but a very dark region, that means no light reaches there at all. A diffused region is, there is partly, light is actually reaching there partly. Alright, so in the same way, moon's shadow has 2 parts. Now, what are they? One is called the umbra. Umbra is the total shadow. This is the inner dark shadow. And when this falls on the earth, a total eclipse occurs. That means at that point where I'm pointing, if you can see my pointer there, that's where the total eclipse occurs. And that is the umbra. That is the total shadow. And the greenish color is the partial shadow, the diffused shadow I showed you. Alright? Now, on those regions you will not see a total eclipse. The partial shadow is called penumbra. Now, this is the faint or diffused shadow, and a partial eclipse occurs when this falls on the earth. Well, let's see if that can be seen with the shadow of, well, I think the umbra and penumbra was very clear with, try and see if you can see if you can watch the difference between umbra and penumbra of the shadow of this. I'm sure you can actually see this. You see the shadow there, and let me just try and make it bigger. Can you see the distinction between umbra and penumbra? The inner shadow, there is the umbra, and the outer is the partial shadow called the penumbra. If the moon's dark umbral shadow sweeps across the earth's surface, then the total eclipse of the sun is seen. And here I have the picture of the gradual setting in of an eclipse. You can see the shadow of the moon begins and it takes over. Now you have a total eclipse. What you now see is the coronal glimpse of the sun. That's a beautiful sight. and now the eclipse is receding. This 9-image sequence captures the essence of the last total solar eclipse in 1999. It's not very common that you see these kind of pictures, and astronomers actually love these kind of days. They will travel to any part of the world if there is an opportunity to see a total eclipse like this. You know why? Because they can actually obtain many valuable information about the sun, because very often you cannot cover the sun completely. When the shadow of the moon, when the moon covers it almost fully, you can get a lot of information from the remaining light that comes out. If an eclipse occurs while the moon is on the far side of it, the moon appears very small and the shadow really does not reach the earth. You see that? If an eclipse occurs when the moon is on the far side, then the shadow really does not reach the earth. Now, this is called an annular eclipse. What you see is an annulus kind of thing. So, if you are within this path, you will see an eclipse where a ring or annulus of bright sunlight surrounds the moon and at the maximum phase of that eclipse. Annular eclipses are also very dangerous to look directly in the naked eye. That means anytime an eclipse of the sun occurs, don't think that, oh, the sun is covered so I can look at it directly. Don't do that. You will spoil your eye permanently. So you got to use some eye shades before you look at it. Annularity can last as long as a dozen minutes, but is more typically about half that length. Since the annular phase is so bright, the sun's gorgeous corona remains hidden from view. Now here, look at the annular eclipse. You can see that annulus, this is the circle that you see as the annulus, and that is due to the annular eclipse. Alright, so these images covers the entire 2.5 hour long annular eclipse on February 16, 1999. Alright, let's talk about lunar eclipse. When does lunar eclipse occurs? Lunar eclipse occurs when the earth is between the sun and the moon and the earth's shadow falls on the moon. So a lunar eclipse occurs on a full moon day when the earth is between the sun and the moon and the shadow of the earth falls on the moon. Now the shadow is actually composed of two cone-shaped components. Well, this is the first cone and this is the second cone, and you see where they intersect. That is the total shadow umbra. This is the umbra and that is the penumbra. The outer or penumbral shadow is a zone where the earth blocks part, not all of the light from the sun. In other words, suns partially will reach the moon. In contrast, the inner or umbral shadow is a region where the earth blocks all direct sunlight reaching the moon. So when the moon is inside the penumbral shadow, partial light reaches there. When it is inside the umbral region, no light at all reaches the moon. A total eclipse, tell me, when will a total eclipse occur? When the moon is in the umbral region of the shadow. A total eclipse starts with a penumbral followed by a partial eclipse and ends with a partial followed by a penumbral. In other words, the moon enters from a penumbral region to an umbral region and then to a penumbral region. that is when you have a total eclipse occurs. Now here you got a sequence of pictures that were taken in the year 2000 of a total eclipse. Well, we have been able to look through the Earth in detail from space. Is that right? The Earth in space, and that gave us a beautiful picture of our Earth. We now know a lot about our Earth as is seen from space. From next lesson onwards, we will look at the Earth, the interior of the Earth, how does the exterior of the Earth look like, and how does the Earth undergo the transformations and changes so that everything that happens on the surface and interior keep changing. Well, that is our theme from our next lesson, and I'll see you for that lesson later on.